Hey everyone, let's learn a little bit from section 4.2, the mean value theorem. Here we're going to learn about Rolle's theorem and the mean value theorem. These are a little bit more theoretical, conceptual concepts involving the derivative. Let's take a look at Rolle's theorem. This is what Rolle's theorem says. If a function is continuous on the closed interval a to b, is differentiable on the open interval a to b, right? That's just a technicality. We never talk about differentiability on a closed interval. And if it starts where it ends, at least on that interval, f of a equals f of b, then there's some value c in the open interval a to b such that f prime of c equals 0. And this is one of these theorems where if I draw a picture of it, I think you'll say, oh yeah, that's obviously got to be true. Right, because if you just choose some points A and B, some x values A and B, then, whatever your function does, if it starts and ends at the same point, maybe right here, well then there's got to be some place, looks like it's right here, where the derivative is 0, right? The slope of the tangent line is 0. It's a horizontal tangent line. I suppose it could have been the other way too, right? Maybe if we had a function, and, it was something like this is A and this is B, and the function went, down or whatever. Still, you have some point, maybe it's right there, where the derivative is 0. Okay? So that's all it says, right? Try to draw a continuous differentiable function without a derivative of 0, right? Where you start and end at the same point. It's not possible. Maybe in this picture I'll just add that, f of a equals f of b. F of a equals f of b. Okay. Now, this might remind you of the intermediate value theorem in that if you want to use it, then you have to verify that we're allowed to use it. We have to show the function's continuous on a closed interval, differentiable on that open interval, and that it's the same value where it starts and ends. So for example 2, show that this complicated function contains a critical point, right? You can go ahead and take the derivative, set it equal to 0, try to solve that out. I don't want to do that. So instead what I'm going to do is say, note that, let's change back to orange. Note that y is continuous on, I'm going to choose the closed interval, -1 to -1 plus 2 pi, right? Because sine is 2 pi periodic. And it's also differentiable on the open interval from -1 to -1 plus 2 pi, right? This is because sine and cosine and whatever, they're continuous and differentiable everywhere, right? You can compose them with continuous and differentiable stuff. We're still good to go. So I'm just choosing these intervals arbitrarily. Now, here's the more important part. Also, I'll say y of -1 equals 0. Do you see that? Because sine of -1 plus 1 is sine of 0, and that's 0. But that's also equal to y of -1 plus 2 pi, because that's sine of 2 pi, which is also 0. By Rolle's theorem, there's some c in the interval from -1 to -1 plus 2 pi, such that y prime of c equals 0. Okay. So y contains a critical point. Okay. Notice that this was a proof. It's sort of similar to the intermediate value theorem, right? I had to verify some conditions, had to plug some values into the function, but then I just stated the conclusion of the theorem, and then that gave me my answer. It gave us our answer, okay? Here's another example. Show that the equation x cubed minus 15x plus 5 has at most one real root in the interval from -2 to 2. Okay? This is a little different. Here we're showing that at most one thing exists, right? We're putting an upper bound on something. Okay? This is going to be a proof by contradiction, where we assume the wrong answer and we show that we get a logical fallacy. Okay? Let's check it out. So first off, we'll say let f of x equal x cubed minus 15x plus 5. So f is, we'll just say, let's not put anything out. Suppose f has 2 real roots, R1 and R2. Maybe I'll write it like this. 2 real roots, R1, which does not equal R2. Okay? We are assuming the thing that's wrong. I'm going to underline this in red because this is wrong. Right? We are assuming something that is wrong. Okay? F is continuous everywhere, so it's certainly continuous on R1 to R2 and differentiable on R1 to R2 open, right? Further, by definition, f of R1 equals f of R2, which equals 0, right? Because that's what it means to be a root. Root means you plug the number in, you get 0. So by Rolle's theorem, there's some c in the open interval R1 to R2, right? Some c between R1 and R2, such that f prime of c equals 0. Okay? But let's take a look at this. What is f prime of c? Well, f prime of c is 3c squared minus 15, which I guess is 3 times c squared minus 5. And I guess if we want to simplify this a bit further, then we can say that this is 3 times c minus root 5 c plus root 5. And we're claiming that that equals 0, right? Does anyone see the problem with that? So in this case, it looks like c would have to equal root 5 or negative root 5, but those two values are outside our interval. Right? That's a contradiction. In fact, really all we needed to know was that they were outside the open interval, right? Because we said that there was a c in this open interval such that f prime equaled 0. Now we're saying, well, actually, no, they have to be outside. This is a contradiction. Since all of our logic was correct, our assumption must have been wrong. So f has at most one real root. A little bit long, a little bit involved, but that's how you do this sort of problem. Okay? So just to point out, we can use, so I changed my notes up a little bit because I thought we had used this example before we hadn't. So the deal is we can use I just want to draw a contrast here, the IVT to show that the equation, right, the intermediate value theorem, to show that this equation has at least one real root. I don't know if that rings a bell. We can use the IVT to find a lower bound for the number of real roots of an equation. Now we use the Rolle's theorem to find an upper bound for the number of real roots of an equation. So let me do one more example here. Show that this equation has exactly one real root. Okay. So first off, we show that there's at least one real root. Then we show there's at most one real root. So, first of all, let's note that let f of x equal 2x plus cosine of x. So, f is continuous and differentiable on negative infinity to infinity, and that means on all subintervals, okay? I'll say since f of, f of negative 10 is less than 0 and f of 10 is greater than 0, I should say by the IVT, f has at least one real root on the interval from negative 10 to 10. Of course, you could be more precise than that, but we don't care about precision. Not for this problem. Alright, so this part here was the IVT. Now we're going to use Rolle's theorem. Now, this might seem familiar. Suppose f has at least two real roots R1 and R2 that are distinct. All right, we've already shown that f is continuous and differentiable. We already said it. We don't need to say it again. So f of R1 equals f of R2, which equals 0. By Rolle's theorem, there's some c in the open interval from R1 to R2 such that f prime of c equals 0. But wait a minute. F prime of c also equals 2 minus sine of c. And that shouldn't make any kind of sense, right? Because sine is bounded by negative 1 and 1. So there's no way that that 2 minus sine of c could equal 0. Right? So you can't have something greater than or equal to 1 that also equals 0. This is a contradiction. So f has at most one real root. Okay, so this right here was Rolle's theorem. Right? Also note that we showed here that there was at least one real root. Now we showed, by Rolle's theorem, there's at most one real root. Okay? So if it has at least one real root and at most one real root, so it has exactly one real root. Okay? A little bit long, right? It's a two-parter. I wouldn't ask the IVT part on the 4.2 part of the exam, but I could ask the Rolle's theorem part. And I could ask the IVT part on the 2.5 topic of the exam, right? All right, next up, we're going to get to the mean value theorem in the next recording.